This presentation is delivered by the Stanford Center for Professional Development.
Today we're going to continue with our discussion of the DFT. This is getting to know your DFT, your discrete Fourier transform. Now, the subtitle, I would say, actually for this, should be, you already know it. All right? The point of the way we're talking about the discrete Fourier transform is that it can be made to resemble the continuous Fourier transform in a great many ways. So the intuition that you built up for the continuous Fourier transform, the formulas that you've learned to work with, and so on, really all have analogs in the discrete case. Now, not in all cases, all right? There are some things that don't quite match up, and that's interesting too. But to realize what doesn't match up so carefully, and to realize why it's interesting, I think goes along with seeing in many ways how much things are the same. All right. So we're going to take the point of view that I'm going to try to make to take the route to make the discrete Fourier transform look as much as possible like the continuous Fourier transform. That's our point of view. It's not, you don't have to do it this way, but I think it's most satisfactory, and again, it allows us to leverage off of what we have done in the continuous case. All right, now, before doing so, let me recall the definition. Here's the definition, and where we ended up last time was sort of a definition that where the continuous case, the idea of sampling a continuous signal to get a discrete signal, sampling its Fourier transform to get a discrete Fourier transform, all that had pretty much vanished by the final definition. So the definition that we ultimately had makes the continuous case almost invisible, vanish. It looked like this. You have a discrete signal so I'm using sort of both the signal notation and vector notation here, and I'll continue to do that to sort of mix the two up because I think they're both useful. So the idea is you have either, you can think of this as an n tuple of numbers or a discrete signal whose value at the nth point is just the nth component here, fm. Okay? Oops, that doesn't look very, it's not much of a statement. And so you can either consider it as a signal as a discrete signal that's defined on the integers, or the integers from 0 to n minus 1, or you can think of it as an n tuple or as a vector. So you have a discrete signal, and its Fourier transform is another discrete signal. It's DFT. Is the discrete signal. I'll call it capital F, but I'll also use the notation to make the connection with a continuous case, a script F with a little underline under it indicating that it's supposed to be a vector quantity or something a little bit different from the continuous case. And it's defined by its nth component. So the nth component of the Fourier transform is the sum from, say, n equals 0 to n minus 1 of the nth component of f times e to the minus 2 pi I n m over n. All right, so everything is defined here in terms of the indices in the exponential, and these are the values of the function, values of the discrete function at the index points, f of 0, f of 1, f of 2, and so on. All right, that's the definition. And they say you don't see at all the fact that in our derivation, this came from starting with a continuous signal, sampling it, sampling the Fourier transform, and then somehow ultimately leading to this definition. Here it's just as an operation on discrete signals, one discrete signal producing another discrete signal. And that's pretty much how we're going to deal with it. All right, but before embarking on that path forever, I want to have one nod back to the continuous case, all right, and talk a little bit about how the DFT is employed and the kind of things you have to know when you're going to use it in practice, as you already have to some extent, and you certainly will more in the future. So one look back at the continuous case to talk about one sort of phenomena of reciprocity that comes, the reciprocal relationship between the time domain and the frequency domain that comes up also in the discrete case. All right, so one more look back. At the continuous case, the continuous roots of the DFT, and reciprocity. Reciprocity of the two domains, time and frequency. All right? So how did it work? We have a signal in the time domain that we discretize, and we have the signal in the frequency domain that we discretize. So imagine that you have two grids. You have a grid in the time domain. You have n sample points, say, that are delta t apart. All right? N points. Wait one second. I'm running out of room to write things, so let me just write it here and then write some of the notation up above. And this is the frequency domain. And we have spacing in the frequency domain, say, delta s apart. All right, so I have n sample points, t0 up to tn minus 1, spaced delta t apart. And n sample points in time, that is. And we have n sample points in frequency. S1, say, or S0, say, up to Sn minus 1, spaced delta S apart. All right, so there are three quantities here. There's the spacing in the time domain, the spacing in the frequency domain, and the number of points, number of sample points, n. And there's a relationship between them. So you have three quantities. Quantities of interest. Delta t, delta s, and n. And they're not independent. Okay, they're not independent. That's the important point. All right, let me remind you of, again, I'm not going to go through the derivation again, but let me remind you what the relationship is. All right, we had at n delta t, that's the spacing in the time domain that has to be, I have to make sure I get this right. I want to say this right. Is L, that's the spacing in the time domain. I want to use the notation I used last night. This is the sort of a time limitedness. All right? And we had n times delta S is the band limitedness that we called that 2b. Okay? That was the band limitedness, bandwidth. All right? So delta t times delta S is equal to, delta t is L over n times 2b over n. That's L times 2, that's 2bl over n squared. But you will recall that when we set up the sampling, 2 times b times L was equal to n, the number of sample points. This is n over n squared. That is 1 over n. Okay? The way we did the sampling, sort of making this not completely justifiable, appeal to the sampling theorem and so on, gave us a relationship between how you sample in the time domain, how you sample in the frequency domain, the number of sampling points you took, and it was exactly that 2bl was equal to n. It was sort of surprising, or not clear a priori, that if you carry out this procedure of sampling in the time domain and sampling in the frequency domain, you're going to take the same number of sample points in both domains. But that's what we found. All right? There's a relationship there. So here, let me highlight it. That is delta S delta t, or delta t delta s, is 1 over n. All right? The spacing in the frequency domain and the spacing in the time domain are reciprocally related to the number of sample points. All right? This is a so-called reciprocity relationship. All right, now, this again has practical significance and practical consequences when you're applying the DFT. You can imagine you have a continuous signal, you want to sample it. What can you choose and what is forced upon you? All right, well, you can imagine choosing how frequently you sample, right? That's the delta t. And you can imagine how many measurements you make, how often you sample, how many samples you take, which is n. All right, so you can imagine choosing delta t, that's how frequently you sample, with a sampling rate, and n, the number of samples. All right, and if you do that, once you do that, then delta s is fixed. Then delta s is determined. The spacing in the frequency domain is determined. That is to say, maybe one way of putting this is the accuracy of the resolution, or how fine the resolution is in frequency, is fixed by the choices you make in the time domain. All right. So let's say I don't know how should we say, the resolution in frequency is determined, is fixed by the choices you make in time. All right. Conversely, you could say I want a certain accuracy or I want a certain resolution in frequency. I want delta s to be fine. I have a certain fineness. That's going to determine then how many sample points I want to take and how I space them in the time domain. Or at least you have to choose two of those things, and the third one is determined. All right. And you can imagine if you're doing this with real data, you have a certain freedom here, but the freedom also carries with it certain restrictions. Ain't that life? Ain't that the way things go? The freedom you have typically is how many measurements you make and how frequently you make them. All right. And once you do that, then that determines what the resolution is like in the frequency domain. And there are ways of getting around this. There's sort of zero padding and sort of special not getting around it, but there's sort of ways of understanding it or massaging it. So-called zero padding, you have a problem on that, and you'll have other chances to experiment with that and other sorts of things. But it's built into the system, all right. And this is a relationship. This sort of reciprocity relationship is another example of the same sort of thing we've seen so many times in the continuous case, now carried over to the discrete case. The sort of stretched in one domain means shrunk in the other domain, or reciprocity between time and frequency. All right, as I say, we've seen many different instances of that in the continuous case, and here's an example of how that carries over to the discrete case. All right, so I wanted to say that because it is the sort of thing that you meet, and you have to understand when you actually apply the DFT in most common contexts where it's associated somehow with some sort of continuous process that you're sampling. You want to take the Fourier transform, you don't have a formula for it, you have to use numerical algorithms to actually compute it, and that means you're sampling, and these the reciprocity relationship puts certain restrictions or limitations on what you should expect to get. Okay. All right, so that is my final nod, at least for now, back to the continuous case. So let's go back now into the discrete world and pretty much stay there. Okay. So back to this formula and its consequences. Let me erase it and then write it down again. Back to the discrete world. The discrete setting. And again, my goal here is to make the discrete Fourier transform look as much as possible like the continuous Fourier transform. So here's how to do that. I want to make the DFT and associated formulas look like the continuous case. So maybe I should say we're not really abandoning the continuous case, but we're doing it, we're situating ourselves firmly in the discrete side of things. All right, now, to help out in that, partly it's a matter of notation. Even more so, it's what you do with the notation and the consequences of thinking about things a certain way. So the first thing I want to do is introduce a symbol, introduce a way of thinking about the exponentials that occur in the definition of the DFT. All right, so let me write down the formula one more time. So again, f is a discrete signal, f0 up to fn minus 1. And its Fourier transform is another discrete signal whose mth component is given by this formula. Sum from n equals 0 to n minus 1, the nth component of f, little f, times e to the minus 2 pi I nm over n. Okay. That's a 2 pi I. All right, the first thing I want to do is introduce a notation. I want to view these complex exponentials as themselves coming from a discrete signal, as values of a discrete signal. This turns out to be a very helpful thing to do for a number of reasons. It gives you a compact way of writing things. It also gives you a way of enunciating certain properties of the Fourier transform that would be very, of the discrete Fourier transform that would be very difficult to do otherwise. So I want to realize the complex exponentials that come in the definition here as arising from also a discrete signal. The discrete or vector complex exponential. Vector, either people refer to it as a discrete complex exponential, the vector complex exponential. You pick what you want to call it. So let me give you the definition. I'm going to write, I'll leave that board up there. So let me write it over here. I'm going to write omega as a vector or as a discrete signal to be the n tuple of powers of the complex exponential that appear in the definition. All right, so the zeroth coefficient, the first entry is 1. That's e to the 0. All right. Then it's e to the 2 pi I. All right, there's a minus sign up here, so let me define in terms of a plus sign, then I'll start taking powers to get a minus sign, all right? So e to the 2 pi I over n, you'll see where this is going from in just a second. E to the 2 pi I times 2 over n, and so on, all the way up to the final term. The nth term is going to be e to the 2 pi I n minus 1 over n. All right? That's the basic vector or discrete complex exponential. So its mth component, so omega, the mth component of this is e to the 2 pi I m over n. Okay? Doesn't take a great leap in the imagination to do this. All right, now I want to define powers of this. Powers of omega. All right, this just collects in one place the powers of the complex exponential that appear in the definition of the DFT up to the minus sign, but it views it slightly differently, itself as a discrete signal. So you can either view it as an n vector or you can view it as a discrete signal defined on the integers from 0 to n minus 1. I want to take powers. Now you say to yourself, what does it mean to take powers of a vector? Well, it doesn't make sense to take powers of a vector, but if you believe in MATLAB, it does, I suppose. And it certainly makes sense to take powers of a discrete function. So omega to the, I want to use the same notation I have in the notes here. Omega to the n is just the discrete signal whose entries are the nth powers of the entries of omega. So it's 1 e to the 2 pi I n over n, e to the 2 pi I 2 n over n, up to e to the 2 pi I n minus 1 over n. And of course, if I can take positive powers, I can also take negative powers. N is not meant to be either restricted to be positive here. But just to write it down, omega to the minus n, same thing, is 1 e to the minus 2 pi I n over n e to the minus 2 pi I 2 over n, 2n over n, then all the way up to e to the minus 2 pi I n times n minus 1 over n. Just replacing n by minus n. Okay. So with this notation, the Fourier transform, the discrete Fourier transform looks a little bit more compact. It's not the only reason for doing it, but it's not a bad reason for doing it. So with this notation, or defining the vector, the discrete complex exponential this way, we can rewrite the definition of the Fourier transform, the discrete Fourier transform. So with this, you can write the DFT as the Fourier transform of f, the nth component, or the nth component, is the sum from n equals 0 up to n minus 1 of the nth component of little f, the function you're operating on, times omega to the minus n, the nth component of that. I haven't done anything different here. I've just rewritten in terms of this discrete vector exponential. Omega to the minus n of m is the nth entry of that quantity. So omega to the minus n, the mth component of this is e to the minus 2 pi I m n over n. Okay? Or, let me put my underlines there so we realize we're taking a discrete case here. Everything is discrete. Or even more compactly, this is the Fourier transform evaluated at m. The Fourier transform of f, sort of written just as an operator, is the sum from n equals 0 up to n minus 1 of f n, the values of the signal you're inputting at n times omega to the minus n. All right. This expression is nothing but this expression evaluated on the index m. Now, I actually find this actually a pretty convenient way of writing the DFT. You know, it's a question about when you write your, it's always a question in this subject, whether it's a continuous case or the discrete case, when you write your variables, when you want to avoid writing your variables. And the same sort of thing applies in the discrete case as well as the continuous case. So this is sort of as far as you can go in writing the DFT without writing variables. All right, in this case, the variable that we're not writing is the mth index. That again, this expression is nothing but this expression evaluated at the index m, or evaluated at the component, finding the mth component. Okay. Now, so we're going to work with this expression a fair amount, or the expression evaluated, and try to make the, so this is about as close as you, this is probably about as close as you can make the discrete Fourier transform look like the continuous Fourier transform. The integral is replaced by the sum, the continuous exponential e to the 2 pi I, or minus 2 pi I st in the continuous case is replaced by the discrete exponential. You know, that's about as close as you can get. And it's pretty close, actually. For a lot of practical purposes, for a lot of computations, for a lot of formulas, it's pretty close. We're going to make a lot of use of it. Now, I told you last time that there are just lots of little things that you have to kind of digest, most of which are analogous to properties in the continuous case. So I'm afraid that what I have to do now is just really go through almost a list of different points, little points that come up, and I can't do all of them. So again, as I pleaded last time, that I want you to read through the notes and sort of hit those points, some of which we'll talk about, some of which we won't talk about. And I decided actually to reorder things slightly from the notes, just so for a little variety here. So I want to derive I'll derive all the same formulas. Nothing's going to be different, of course. But I want to do it from a slightly different tack. I mean, I like the way actually I wrote it all out in the notes, but that does take a little more time. And I wanted to, here in class, try to sort of hit the high points a little bit more quickly. All right. So again, there's no way of getting around this. We just have to have a certain list of properties that that come out as consequences of that formula that we need in order to be able to sort of use the DFT day to day. So the very first ones are just mini properties, little properties. The first one actually is something I'll mention it now, but I'll talk about it next time. Is something that's different between the discrete case and the periodic and the continuous case, and that is the periodicity of the inputs and outputs. All right? That is, so I'll do this next time. I'll talk about this next time. But I wanted to mention it here because it really is sort of the first thing, probably the first thing you should establish about the DFT. And here, despite all my big build-up about how similar they are, this is a difference, actually. Between continuous and discrete cases. Now, what I mean by this, and again, I'll say this in more detail next time, is that initially you have a discrete signal you feed in, and you get a discrete signal out. You have a signal defined from index from 0 to n minus 1. The signal that comes out of that is also indexed from 0 to n minus 1. But as it turns out, you are really compelled by the definition of the DFT to extend those signals to be periodic of period capital N. That is to say, to be defined on all the integers. So we'll leave that up there because it really depends on the formula. The definition of the DFT compels you to regard the input little f and the output capital F, its discrete Fourier transform, as not just defined on the integers from 0 to n minus 1, but as periodic discrete signals. Of period n. All right? That is so because the vector exponential itself turns out to be naturally a periodic signal of period n. Discrete periodic signal of period n. But again, I'll do the details next time, but I just wanted to highlight this because this is sort of the approach taken in the notes as the first thing you do. And it really is, in some sense, properly the first thing you do, but I just wanted to arrange things a little bit differently, hit some of the cool high points. So this is so because omega itself, this discrete complex exponential, is naturally a periodic discrete signal of period n. Okay? And more on this next time. This actually turns out to have significant consequences. The fact that you really have to, it's all, whether or not you use it in a particular problem in a particular setting, it's lurking in the background. That the input signals are periodic and the output signals are periodic. And in some cases, actually, it has consequences for computation. All right, some computations, if it's not taken into account, you can get results that are not in accord with what you might expect. And it usually has to do with not taking in proper account of the periodicity. Sometimes you have to shape the signal a little bit differently to take that into account and so on. So more on this next time, but I did want to mention it. The main thing that I want to talk about today is the orthogonality of the complex of the vector of the discrete complex exponentials. And its consequences. So two, the other sort of little fact, not so little fact actually, is the orthogonality of the discrete complex exponentials. All right, most sort of non-trivial or slightly less than trivial, most interesting properties of the DFT can be traced back to what I'm about to talk about now. I'll put that in quotes. properties of the DFT involve this. Involve this property. Now, what is the property? Okay, so let me give you a setup, and I'll tell you what I mean. This would be harder to, or not as couldn't be formulated in as easy a way if I didn't introduce this vector complex exponential. If I stayed writing just the exponential terms themselves, e to the 2 pi I, blah, 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 then it would be a little more difficult, a little more awkward to formulate the property. But if you introduce the discrete complex exponential, there's a very nice way, very nice property that they have that turns out to be very important for a number of reasons. All right, so again, omega is 1 e to the 2 pi I over n up to e to the 2 pi I n over n minus 1, sorry, over n. And the powers that we look at are omega to the k, say, is 1, e to the 2 pi I k over n, e to the 2 pi, I'll write one more term out here, 2 pi I 2k over n, up to e to the 2 pi I k times n minus 1 over n. All right? The orthogonality of the discrete complex exponentials is really the orthogonality of the powers of these complex exponentials. That is to say, if k is different from L, then omega to the k and omega to the L are orthogonal. Now here, when I say they're orthogonal, I mean not so much thinking of them as discrete signals, but thinking of them as n vectors. All right. Now, I want to show you why that works. And also what happens when k is equal to L, because that's where much heartache comes. All right. So let's compute omega to the k. So to say they're orthogonal means I have to compute their inner product. All right. We haven't looked at inner products much since the very beginning of the course when we talked about Fourier series, but they're coming back now. And I'll remind you of the definition in this particular case. So I'm taking omega to the k dot omega to the L. It's a complex inner product. It's the inner product of these two vectors. So what is that? That's the sum from, say, n equals 0 to n minus 1. Let me write it out in terms of, let me just write it and then I'll say more about it in a second. That's the nth component of omega to the k times the nth component of omega to the L conjugate. All right. If I use this notation to indicate the nth component, then the inner product of two vectors is the sum of the products of the components. But when the complex inner product, you take the complex conjugate of the second term. All right. So what is this? This is equal to the sum from n is equal to 0 to n minus 1. Let me write in terms of the complex exponentials now. E to the, I mean, the usual complex exponentials. E to the 2 pi I k n over n times e to the 2 pi I L n over n conjugate. Which is, just puts a minus sign in the second complex exponential. Keep me honest on my algebra here so I don't make any slips. So that's the sum from n is equal to 0 to n minus 1 of e to the 2 pi I k n over n times e to the minus 2 pi I l n over n. All right? And you have to realize that what you have here is a geometric series. That is, this is, let me write this a little bit differently. This is the sum from n is equal to 0 to n minus 1 of e to the 2 pi I k minus l raised to the nth. All right? Kn, divided by n, sorry. K minus l divided by n. divided by n, all raised to the nth. All right, exponentials being what they are. This is e to the 2 pi I, kn over n, e to the 2 pi I minus e to the 2 pi I ln over n. I group those terms, 2 pi I k minus l divided by n raised to the nth power. That's a geometric series. Finite geometric series. And we know what its sum is. Okay, we know how to sum that. So if k is different from L, if k is not equal to L, then this sum is equal to 1 minus e to the 2 pi I k minus L divided by n raised to the nth power. Let me write it like this. Divided by 1 minus e to the 2 pi I k minus L divided by n. Okay? Nothing on my sleeve. Make sure I did this right. I believe so. Make sure I wrote it neatly enough. So it's, 1 plus r squared plus r cubed up to r to the n minus 1, where r is this exponential. All right? So it's 1 minus the thing to the nth power. I have n terms. 0 to n minus 1 is n terms. Raised to the nth power, divided by the thing that's getting raised to the power. 1 minus the thing that's getting raised to the power. There's no problem with the denominator here because k is different from L, and k minus L is always less than n, so these are distinct. This is never equal to 1 down below. But on top, if I raise it to the nth power, it is 1 minus e to the 2 pi I k minus L divided by 1 minus e to the 2 pi I k minus L divided by n. All right? K minus L is an integer. E to the 2 pi I k minus L is 1. So this baby is 0. So if k is different from L, omega to the k dot omega to the L, the inner product of the discrete complex exponentials is equal to 0. What happens if k is equal to L? What happens if k is equal to L? If k is equal to L, go back to the sum here. All right? If k is equal to L, then I'm getting e to the 0. So I'm just getting a sum of a bunch of 1s. How many 1s do I have? N of them. All right? So if k is equal to L, omega to the k dot omega to the L is equal to n. All right? To summarize, omega to the k dot omega to the L is equal to 0 if k is different from L, is equal to n if k is equal to L. In the notes, this is done a little bit more generally because I allow for periodicity. And instead of saying k is equal to L or k is different from L, you say k is different from L modulo capital N. Here you say k is equal to L modulo capital N. Doesn't really, that follows out from the general discussion. We'll get to that next time. But this is the first sort of encounter with it, and this is probably the easiest way of thinking about it. All right, and it's an extremely important property. The orthogonality of the vector exponentials. Now, it's a fact, or it has been a fact, tradition in the electrical engineering department. I say this, listen very carefully. It's a quals tip. All right. Bob Gray, my dear colleague Bob Gray, used to always ask quals questions that somehow reduced to the orthogonality of the discrete complex exponentials. Somehow that was always involved in his quals question. All right. So now you know. I don't know if he still does it since I've been making a big deal out of this the last couple of years. All right. But somehow he would always manage to ask a question that reduced to this or somehow involved this in a crucial way. All right. It's very important. Now, the thing that makes Now here's another difference between the continuous case and the discrete case that shows up in a lot of formulas, and it leads to much heartache and much grief. All right? The fact that they're orthogonal but not orthonormal. All right? The length of the vectors is not n, it's not 1, it's the square root of n. All right? What this says is, to put this another way, the length, the norm of this vector exponential, discrete complex exponential, is the inner product of the vector with itself. So omega k squared is omega to the k dot omega to the k, and that's equal to n. So the length squared is n. The length is equal to the square root of n. This fact causes an extra factor of n, or 1 over n, to appear in many formulas involving the DFT. It can all be traced back to this. It is a royal pain in the ass. I'm sorry to have to report that to you, but it is, and it always traces back to this. Causes a factor of n, or 1 over n, to appear in many formulas. All right, sorry. The way we define the DFT, it does. There are ways of sort of getting around it, but it's sort of awkward. And once again, like in most things, there's no particular consensus as to what is best here. But the way we're defining the DFT, which is pretty standard, you have this sad fact that they're orthogonal, the vector complex exponentials are orthogonal, but not orthonormal, not quite orthonormal. All right, and it causes that extra factor to come in. Now, let me give you the first important consequence of this. The first important consequence of the orthogonality of these discrete complex exponentials is the inverse DFT. So a consequence of the orthogonality is a simple formula for the inverse DFT. All right, now, again, in the notes I did this a little bit differently. I mean, I wound up with the same formula, but I did a little bit differently and I sort of liked it, again, because it was a way of discovering what the formula should be, independent actually of the discrete complex, although that comes into it, of the orthogonality of the discrete complex exponentials and so on. But again, just to do things a little bit differently so you have two different points of view here, let me just give you the formula and show why it works. Now, I don't like doing that because I don't like this sort of deus ex machina aspect of it, where you write down this formula and say, son of a bitch, it works. I sort of instinctively don't like that, but I'm going to do it anyway. Son of a bitch, I'm going to do it. All right. And that is, because I want to show you how it's a consequence of this orthogonality relationship. It's quite nice. All right. Here's what we find. The inverse DFT is given by the inverse Fourier discrete. I'll just write down the formula. I'll write it over here. It's full glory. Again, I'll put an underline under it. So again, apply to some signal f is the mth component of that is 1 over n times the sum from n equals 0 to n, capital N minus 1 of little f at n. And this time you take positive powers, e to the plus 2 pi I n m over n. Or, written a little bit more compactly, in terms of these vector exponentials, the inverse Fourier transform of f is 1 over n at m is 1 over n times the sum from n is equal to 0 to n minus 1 of f n omega to the n, its mth component. Same thing, omega to the positive power n. Or written more compactly still, if I drop the variable, inverse Fourier transform of f is the sum from n is equal to 0 to capital N minus 1 of fn times omega to the n. Okay? Oh, I forgot the painful factor 1 over n. All right? So this is as close as you can get for the inverse discrete Fourier transform to look like the inverse continuous Fourier transform, and the difference, among other things, is this irritating factor of 1 over n. And it comes in there exactly because the vector complex exponentials are orthogonal but not quite orthonormal. Okay? But now I'll show you why it works. I'll show you why this is the inverse. Again, if you look at the discussion in the notes, this formula emerges from an analog of the continuous case. All right? You talk about reverse signals and duality and all those things we're going to talk about. Well, maybe not talk about all of them, but I want you to read all of them because it's another series of little points that you have to sort of digest. And if you do that, if you pursue the analogy with the continuous case via duality and all the rest of that stuff, this formula emerges quite nicely from that. All right, independent of first talking about the orthogonality of the vector complex exponentials. But since we've done it this way, let me show you how they come in. All right, so I have to show you, if I have time here, that the inverse Fourier transform of the Fourier transform of f is equal to f. Okay? Or I have to show you the inverse Fourier transform of the Fourier transform. We put a variable in here. At the nth component is the nth component. Okay? That's what it means for the thing to be the inverse Fourier transform. Okay, so let's do that. We have no recourse here other than to appeal to the formula. And I want you to see how this orthogonality comes in. I have to be careful with my indices here. So the inverse Fourier transform of the Fourier transform of f is 1 over n times the sum at m is 1 over n times the sum from n is equal to 0 up to n minus 1 of the coefficients of the thing I'm putting into it, which is the Fourier transform, times omega 2, maybe I'll put it right in terms of complex exponentials here, times e to the 2 pi I n m over n. Right? Okay. Right? Is that correct? That's what the inverse Fourier transform looks like that? Right. Okay. Okay, now I have to bring in the formula for the Fourier transform. I'm just sort of debating in my own mind here, which you can't hear, whether or not I should write it in terms of the complex exponential or write it in terms of the omegas. I started with this, so I'll keep this up. It may be a little cleaner if I use the other notation for it, but never mind. Let's go forward. So now I have to write this sum from n equals 0 up to capital N minus 1. So I need to bring in the formula for the Fourier transform. That's the sum, say, of k equals 0 up to n minus 1 of f of k. The nth component of the Fourier transform is the sum from k equals 0 to n minus 1, f of k e to the minus 2 pi I k n over m, capital N, and then times e to the 2 pi I n m over capital M. Check me. Make sure I haven't slipped anything past you here. Did I remember my factor of 1 over n in front? I did. Okay? All right, so once again, all I did here was substitute the formula for the Fourier transform. The nth component of the Fourier transform of f, the discrete Fourier transform of f, is this sum. Right? The power here, n, means I'm taking the nth component of the Fourier transform of little f. Good. And now you can combine everything here. What I'm going to do, guess. I'm going to swap the order of summation. Well, I'm going to put everything together and then swap the order of summation. So that's the sum from, it's 1 over n times the sum from n equals 0 to k equals 0. 1 over n. Sum from n equals 0 to n minus 1. Sum from k equals 0 to n minus 1. F of k times e to the 2 pi I n k over n times e to the 2 pi I nm over n. And I see I got this wrong. This is a minus here, right? Minus. Okay. Okay. Now, swap the order of summation. It's like swapping the order of integration, a technique we use many times. All right? So this is 1 over n, sum from k equals 0 of the sum from L and the sum from n equals 0. Now this depends only on f of k, does not depend on n, so I'm going to bring that out of the sum. F of k times the sum from n equals 0 up to n minus 1. And what remains are these products of complex exponentials. E to the minus 2 pi I nk over n times e to the 2 pi I nm over n. Okay? Wonderful. You have to have a certain taste for this. Okay? Now, what you should recognize in that sum is the inner product of, this is the powers of the complex, vector complex exponential times its conjugate. All right? E to the plus 2 pi I nm over n, e to the minus 2 pi I nk over n. It is the mth vector complex exponential the mth power inner product with the kth power. All right? That's what this sum is, summed over n. All right? The kth power of omega inner product with the mth power of omega. And that is either equal to 0 if m is different from n, m is different from k, or n if m is equal to k. So that sum, n equals 0 up to n minus 1 of e to the minus 2 pi I n k over n times e to the plus 2 pi I n m over n is either equal to 0 if k is equal to m, and it's equal to n if k is different from m, and equal to n if k is equal to m. Okay? All right, so only one term survives here, and then it's the outside then it's the outside sum here. So the only term that survives is when k is equal to m. In which case you get n times 1 over n times, and if the only term that survives is when k is equal to m, you get f of m. And we're done, about. So only surviving term is k equals to m, and you get the inverse Fourier transform of the Fourier transform of f at m is equal to f of m. And that is to say, the inverse Fourier transform given by this formula really is the inverse of the Fourier transform. Okay? Works like a charm, and it depends crucially on the orthogonality of the complex exponentials. Crucially on that. Like many other properties. And the only thing that makes it a little bit painful is this extra factor of n that comes in, but that's just life. That's just the way it goes. Okay, that's it for today. Next time, we'll do more little interesting facts about the DFT.